The third example for symmetry is a really interesting one, and we will be using this problem later on. So it's good to already learn some things or some characteristics about this model. Now what we are looking at is a plate with a hole. It's a very common structural member that you will see time and again during your courses at aerospace or at mechanical engineering. Now this plate with a hole is represented with a planar geometry in this case, and therefore it has a certain thickness which is just a number that can be input into the finite element model. Now if you look carefully at this the geometry that's provided to you, then you have a certain length of L and a breadth of B, and the central slot is given to you with a certain radius, which may be R, and it's present exactly at the center of the plate. The load that's applied on the two sides are exactly the same. So what you don't see here are the boundary conditions. So this is a very classic problem, and there are certain ways to deal with it. And what basically you want to see is a behavior such that once you start applying the load P Newton per millimeter, which is a distributed load on both the edges, your plate will start basically expanding in both directions, and you will see a certain final shape under this load, a bit exaggerated here, which looks somewhat like this. So your hole will become elliptical, not circular anymore, and your plate would have stretch. That means you have a Poisson effect, which is pushing the plate inwards right here. So there are certain ways of solving this problem in terms of symmetry. Now let me draw very quickly the geometric axis, so it's easy for us to visualize. So we have X and we have Y. Now we can see that this is also this geometry is symmetric also about the y-axis, like every other geometry we dealt with now, because the loads that are applied on both sides are exactly the same, and the geometry also on both sides are identical in terms also of numbers. So what we can do is we can now draw this out on the right hand side first as a step one. So we see that we are sorry about this bad picture. So your geometry now reduced on the right side looks like this, and you have a certain load that is acting on it, which is intact because it's a distributed load, so I will not change anything about it, so no updates to the load. But your geometry has changed, and then you will need updated boundary conditions. Now we know that it should not be moving perpendicular, but it can move in the direction, so therefore we know that all through this edge there will be a roller support which will be added. And if you remember, the deformed shape has to be in this direction, so it should, of course, all the nodes should be allowed to move in the direction of the axis that is used for symmetry. Now if you keep looking at this problem, you will also notice that there is a second axis of symmetry, which is basically the x-axis. So you can also divide this structure into another half. So the second step of symmetry is just keeping the top intact, somewhat like this. The load still remains the same because it's a distributed load. This part still has a roller support condition as before, and what happens now is that we need to apply a new boundary condition at this edge. As per our principles before, it should not be allowed to move perpendicular to the axis of symmetry, which is the x-axis, so we shouldn't let it move in this direction. However, it should be allowed to move in the axis of symmetry, so we make it a roller support here as well. And basically that's exactly what completes our problem. So we have been able to reduce this problem to such a small one, so our number of elements are actually becoming 1/4 just by adding very smartly some extra constraints at the correct edges. So that's it with this example. See you at the next one.